right, so when you take the derivative of this and set it equal to 0, you'll get your critical numbers. We should write that as an x to the 1/2. And then the derivative looks like half of 6 is 3. 1 power less gives me a negative 1/2 power.
Yeah.
And then over here, I get a -8. Now let's write that with positive exponents. That puts the x to the 1/2 underneath the 3. Oops, I said underneath the 3, and it didn't do that. So having the x on the bottom automatically makes x is equal to 0 a critical number, but this says that x is 0 is going to be a critical number anyway because it's an endpoint. It's an endpoint of that graph as well. So we hang on to x is 0, and now we are setting this equal to 0, and we're going to solve for x. So what I typically do there is take the term that's negative and move it to the other side. You know what comes next? What would you do next? I want to get the x on the bottom. So how about we multiply both sides by x to the 1/2? Right, get rid of all denominators. And now instead of getting the 3 to the other side, get the 8 to the other side. So x to the 1/2 is equal to 3/8. What do I do to solve for x? Square both sides. Square it over here, square it over here. And so we get a critical number of 3 squared is 9, 8 squared is 64. Now to get the intervals in which it's increasing and decreasing, we break up the number line, remind ourselves that we're starting at 0. And then 9/64, and we want the sign of f prime. So I'm going to write it from here. That's 3 over the square root of x minus 8. So let's find something kind of easy. 9/64 is pretty small, so let me test 1/64. So I'll do it over here. We've got 3 divided by the square root of 1/64 minus 8. We have to decide whether that's positive or negative. What's the square root of 1/64? 1/8. So how do I divide 3 by 1/8? Multiply it by 8, right? So 3 times 8 is 24. 24 minus 8 will be positive. Now an easy test point over here is 1, because the square root of 1 is 1, and that leaves me with 3 minus 8, and that's negative. So my graph will increase between 0 and 9/64, decrease for the rest of time, and that gives us only a relative max. So we got increasing between 0 and 9/64. It decreases to the right of 9/64. Relative max occurs when x is 9/64, and there is no relative min. Agree with that? What else? Are we good on the 4-3 stuff then?
Number 8.
Okay.
Let f of x equal 2x to the 4th minus 4x squared plus 6.
Okay.
It wants the interval where it's increasing, decreasing, the relative max, relative min, where it's concave up, concave down.
We're going to do the whole shebang to this one.
Yeah.
All right. So let's go ahead and write everything out. We want the critical numbers, where it's increasing, where it's decreasing, it has a relative max, where it has a relative min. Then we want the inflection points. Then we want it concave up and concave down. And then we'll even graph it. Okay, so you're going to take the derivative and set it equal to 0. You're going to get 3 critical numbers. So go for it. Let me see if everybody can get 3 critical numbers out of this. Nice 4 numbers. Take the derivative, pull out the greatest common factor, see if anything else factors. And I think you should get x is 0, x is 1, and x is -1. Okay. 8x cubed minus 8x. Factor out the common factor of 8x, leaving us with x squared minus 1. And that factors as the difference of squares. So f prime is 0 when every factor is 0. So 8x is equal to 0 when x is 0. X minus 1 is 0 when x is 1. X plus 1 is 0 when x is -1. So our critical numbers, 0, -1, and 1. So I suspect the shape of this graph might be kind of like a W. We'll get the sign of the derivative. I like to plug things into the factored form so that I don't have to compute anything. So I'll go back to this. So first, let's test x is -2. That makes that factor negative, that one negative, and that one negative. So I've got 3 negative factors multiplied together, meaning that I've got a negative derivative. Now let's test x is -1/2. That makes that negative, but positive. So this time 2 negatives. Give me a positive here. Here I'll use x is +1/2. That makes that factor positive, that one negative, that one positive. So I only have 1 negative factor. And then if x is 2, all 3 factors are positive. So we've got a graph that does look like a W. It goes down, back up, down, back up. So we write the increasing ones, okay? The up arrows occur between -1 and 0, and then again to the right of 1. See if this made the camera here. Scoot that over a notch. Scoot. Yeah. Decreases to the left of -1 and between 0 and 1. So to the left of -1 is written as minus infinity to -1, and then between 0 and 1. Where's your relative max? The arrows, tell me what the relative max is. 0. And the relative mins are the other two. Now let's go to the step before we did all the factoring and see if we can find inflection points. You're going to get 2 points of inflection. Let's see if you can figure out what they are. Take your second derivative and set it equal to 0. I don't think your points of inflection are going to be very pretty. You definitely have 2 of them. Who's got the inflection points?
I'll try plus and minus the square root of 1/3.
Those are them, plus or minus the square root of 1/3. Those are them. Here's the second derivative. 3 times 8 is 24. Then I got an x squared minus 8. We're going to set that equal to 0. So I'll move the 8 over. Divide by 24. And 8 goes into 24 3 times. And now plus and minus the square root of that. If you want, you can take the square root of 1 and write that as plus and minus 1 over the square root of 3. Either way, doesn't matter. But now we're going to take those two numbers and put them on the number line and look at the sign of this guy. So let me do it right here. There's negative square root of 1/3, positive square root of 1/3, and we want the sign of f double prime. So let's see. This number is going to be smaller than, bigger than -1, so I can use -1 as a test point. If I put a -1 and square it, it's +1. So this behaves like 24 minus 8, which makes it positive. And because of the squaring operation, it's symmetric right there. +1 does the same thing. In between those two numbers, I can use x is 0, which wipes that term out, and I get a negative second derivative. Where it's positive, it's concave up. Where it's negative, it's concave down. So those are intervals again. Concave up to the left of -1 over square root of 3. Concave up to the right of 1 over square root of 3. And then it's concave down in between. And if we plot these three numbers, we can get a pretty good graph. So let's go ahead and do that. F at 0 is just the 6. These are even powers. So F at plus and minus 1 will be the same. there'll be 2 minus 4 is -2, plus 6 is 4. The graph goes through those 4s and 0, 6. -1, 4, 0, 6, 1, 4. And then it goes down, up, down. So it's going to come down, get our max, down, and there. And remember, the inflection points are going to be when it changes concavity. So it's just kind of eyeballing it. It looks like about right here and here are the 2 inflection points. Okay. Yes, sir.
To find the exact value of the y-coordinate for the inflection points, do you just plug those into the original f of x
Yeah,
equation?
do they want the y values too? I bet you can just type it in like that. You can just type it in at, let's see, f of 1 over the square root of 3 would be 2 times 1 over the square root of 3 to the 4th minus 4 times 1 over the square root of 3 plus 6. If you type that in, Weber will figure it out for you. What else you got? Okay, we got kind of a big section today in section 1.4, not 1.4. What chapter are we in? 4.4. We're going to talk about finding the asymptotes of a function. A lot of the stuff we did in section 4.3 here is graphing continuous functions. But you know, some functions have breaks and jumps and holes in them. We're going to look at the ones that have asymptotes. Section 4.4, horizontal and vertical asymptotes. We'll do the vertical asymptotes first. So finding asymptotes are what we're going to do first. And then we're going to look at graphing functions. That have cusps. With sharp corners. So when we're talking about functions with asymptotes, most of the functions that fall into that category will be rational functions, things that have a numerator and a denominator. We do have some functions that have asymptotes that aren't rational, like logarithms and exponential functions. But for the most part, these functions have asymptotes. So the first one, we'll look at horizontal asymptotes. No, I said we're going to do vertical asymptotes first. So let's do vertical. Let me go ahead and write this. Horizontal, Horizontal, and vertical asymptotes usually occur in rational functions. With some exceptions. Like logarithms and exponential functions. So we're going to talk about the rational functions that have the form f of x that has some sort of numerator as a function of x and some sort of denominator as a function of x. Something that looks like a numerator over a denominator. Doesn't show up. Let's move that. Move that. I've forgotten how much I love doing this. As far as goes, so let's do. Okie dokie. Okay, a vertical asymptote is a discontinuity. A vertical asymptote is a vertical line that has an equation x is equal to something, some number. A vertical asymptote has the form x is equal to some number. So let me use the letter A for that number. And x is equal to A makes the denominator equal to 0, but not the numerator. The value of x that makes the bottom 0, but not the top. And near a vertical asymptote, here's the x-axis. And let's just put x is equal to A right here. And I'll draw my asymptote like that. Near the asymptote, the graph becomes infinite, either in this way or opposite. This side can go up and that side can go down, or they can both go in the same direction. Maybe both of them up or both of them down. We will describe the behavior of a function near an asymptote with one-sided limits. The one-sided limits will become infinite. This picture says that the limit as x goes to A from the the left-hand side of whatever the function is, that limit goes to plus infinity. And if I come in from the right, then my function drops forever, so we say it goes to minus infinity. This one will be the opposite. The limit as x goes to A from the left goes to minus infinity, and the limit as x goes to A from the right goes to plus infinity. Goes down, and here it goes up. Here, both one-sided limits go to plus infinity. And here I write that both one-sided limits go to minus infinity. We can pretty much get this either by plotting points or by looking at the first derivative. For example, let me give you three functions. F of x is 1 over x minus 2 squared G of x is 1 over x, x plus 1. And h of x is, I don't know, let's put an x up here. So only the first two examples, F and G, have vertical asymptotes. They have denominators that can become 0. The numerators are constant, so they're never 0. This one has a vertical asymptote when x is equal to 2. It's an equation of a line. It's not a point. X is equal to 2 is that vertical line. Because when I put a 2 in here, I get a 0 on the bottom. So now it's your turn. What are the vertical asymptotes of g of x? And -1. This function has no vertical asymptotes, because if we tried to set this denominator equal to 0, setting that denominator equal to 0 gives me this statement, that x squared is -1. And there are no real numbers that we can square to get a negative number. Now we're going to describe the behavior of each function near the vertical asymptote using one-sided limits. So for this first example, I'm going to look at the limit as x goes to 2 from the left, and the limit as x goes to 2 from the right. But I'm going to be helped by the fact that the denominator is squared. Squaring the denominator will always make whatever minus 2 a positive number. So once I get that positive number, I divide it into 1. So that's telling me that these guys are always positive. There's no way these can go to minus infinity. So for instance, if in each of these I plug in 2.1, or something 0.1 away from each of these. If this is 0.1 away, but on the left, that makes it a negative 0.1 in here. 0.1 is 1/10. If I square 1/10, I get 1 over 100. If I divide 1 by 1 over 100, I flip and multiply and get 100. So it gets big real quick when I'm close to 2. So it keeps getting bigger and bigger. We're going to say that one goes to plus infinity. Same deal happens here. If I'm slightly bigger than 2, then I'm going to get something like a 1 over 100 again when I square the 0.1 and both ends go up. So the picture on this one looks something like this. Here's x is equal to 2. Both of the ends of the graph do something like that. If I want to know what happens to the rest of the graph, then I need to look at where the graph is increasing, decreasing, where it has a relative max and min. We'll also need to look at things like where this thing has horizontal asymptotes. So I'll finish that graph later. But that's what it looks like near x is 2. All right, this one has 2 vertical asymptotes at 0 and at -1. X is equal to 0 is the y-axis. So my asymptotes are in here. Here's x is equal to 0, and here's x is equal to -1. So I need to see where the graph is here, where it is here, and where it is here. This time, I'm going to describe the behavior near the asymptotes using derivatives. If I can see where the graph is increasing and decreasing, I can tell you what's happening near the asymptotes. Where'd the camera go? Who stole my eraser? Oh, you little bugger. Okay, so here's what we're going to do to describe the behavior of this. I'm going to think of this as 1 over x squared plus x. And I'm going to use the first derivative information to tell me what's going on with it. I can plot points, but that's kind of painful. So I'm going to look at g of x is 1 over x squared plus x, and I'm even going to write that like this so that I can take the derivative just with the power rule. I'm looking for critical numbers and where the graph rises and falls. So g prime of x, we bring the power down, raise that to 1 power less, and then multiply by the derivative of what's inside, and we get 2x plus 1. When I simplify this, I'm going to keep the minus 1 on top with the 2x plus 1, and then this guy goes on the bottom. So I'm going to get a critical number. That occurs when the numerator is 0. 2x plus 1 is 0 when x is negative 1/2. Now I'm going to look at the sign of the derivative around the critical number and around each asymptote. So here's x is negative 1, here's x is 0, and here's x is, oops, negative 1/2 is on the other side. This one's an asymptote, this one's an asymptote, and that one's a critical number. So I'm going to keep that as a solid line. And I've got 1, 2, 3, 4 intervals on which to check the sign of G prime. So we're going to plug numbers into that derivative and decide whether G prime is a positive or negative number. The bottom factor, x squared plus x, has this squared out here. So I don't have to worry about plugging numbers down there. No matter what I plug in, I'm going to get a positive. So I'm just going to plug stuff in here. So over here, for instance, let's take x is negative 2. Inside the parentheses, when x is negative 2, I get a negative 3. But then I change the sign, making that a positive 3. Divided by positive gives me a positive. Let's take a number between negative 1/2 and negative 1, like a negative 9/10. 2 times negative 9/10 is a negative 18/10. Plus 10/10 gives me a negative number in there, but that makes it now positive. A number between negative 1/2 and 0 will be something like negative 1/4. 2 times negative 1/4 is a negative 1/2. Plus 1 makes a positive 1/2. This makes it back to a negative 1/2. And out here, let's just use x as 1. 2 times 1 is 2, plus 1 is 3. That's positive. That makes it negative. So the graph is going to rise, keep rising, fall, keep falling. That means I have a relative max when x is -1/2. Let's look at what the value of g is at that point. G of -1/2 is 1/(-1/2) times a +1/2. -1/2 times +1/2 is a -1/4. Divide 1 by a -1/4, and we get a -4. So let's put that right here. So just looking in here, in order for that to be a max and the graph to rise and fall, the graph has to do something like this, right? Now looking out over here, the graph has to rise. So to the left of x is equal to -1, the graph has to rise. So it's going to have to go to +infinity up there. Kind of like that, right? Then to the right of 0, the graph has to decrease. So in order for it to decrease, it's got to look like that over here as well, right? So it's going to have to do something like this. Now we can write the one-sided limits. Let's write the two one-sided limits around x is equal to -1. So x goes to -1 from the left. And the limit as x goes to -1 from the right. Your value is either going to be +infinity or -infinity. So describe for me the graph when x is slightly to the left of -1. Which way is the end going? +infinity. That's this piece. Okay. All right. Another choice. +infinity or -infinity when x comes to -1 from the right. That's this piece. Our other asymptote was 0, so let's write the one-sided limits around 0. Limit as x goes to 0 from the left, and the limit as x goes to 0 from the right. What's happening from the left? What are the y values? They're right here, right? They're going down. Those are negative infinities. On the other side of that asymptote, they're going up. So in describing the behavior around an asymptote, you can either plug some numbers in and see if the y value is getting bigger as you get closer, bigger positive, bigger negative, or you can just do the first derivative stuff. Okay. All right, let's look at when a function has a horizontal asymptote. Horizontal asymptotes are lines of the form, well, they're horizontal lines. Horizontal lines have the form y is equal to some number. So I'm going to use a number L. The line y is equal to L is a horizontal asymptote. Gosh darn that thing. Oh wait, let's try that arrow. Hey, look at that, I got it. Here's a horizontal line. Horizontal asymptotes mean the graphs at the very ends will approach that horizontal line. It describes the behavior of the function when x is a really big number or when x is a big negative number. Okay, so we determine the end behavior of a function. That is, we look at the function as the x's are real big numbers, whether they're big positive numbers or big negative numbers. If they tend to a particular value, then that value will be the number L that give us the horizontal asymptote. So on the horizontal line, this is the line y is equal to L. There's a horizontal asymptote at the ends of the graph go there. The middle can do whatever it wants. Let's say the end of the graph goes there. And then whatever happens in here. But the ends of the graph are bounded by that line. And again, most rational functions would have that kind of behavior. Y is equal to e to the x has that kind of behavior as x goes to minus infinity. But most of the time, we're talking about rational functions. So again, f is going to be a function that has the form, some sort of numerator and some sort of denominator. When x is a big number, if the numerator grows faster than the denominator for a very large x, then there's not going to be any asymptotes. If the numerator grows faster than the denominator, then the ends of the graph will get real big. Big negative, big positive, right? So if the numerator grows faster than the denominator, then there will be no horizontal asymptotes. For instance, this function. The denominator grows on powers of 3. The numerator grows on powers of 3. The denominator only on powers of 1. So if x is a big number like 100, 100 cubed is going to be much bigger than 100. Or even 101. Okay, the degree is bigger on top than on the bottom, then there are no horizontal asymptotes. The ends of the graph will either look like that, or one end up and one end down, and in any permutation. For an x cubed, we're used to the left end down, the right end up, right? So we're going to look at the cases where the numerator has a smaller degree than the denominator, or where the numerator has the same degree as the denominator. Those are the cases that give us horizontal asymptotes. So let's just look at your most basic function. This is one of the functions in chapter 1 that I said, know the graph. What does the graph of y is equal to 1 over x look like? Anybody draw the graph of y is equal to 1 over x? What's it look like?
It goes like that.
Here?
Yeah.
Is that what you described?
Yeah. And then like that. Over there.
Negative over there, right? So the vertical asymptote we knew was going to be at x is equal to 0. Now look at the ends of the graph. Way out here, when x is a big negative number, put a big negative number in here, divide that into 1, and you get something pretty darn close to 0. Put a big positive number in there, same thing happens. 1 over x goes to 0 as x gets big from any side. 1 over x goes to 0 when x itself is real big. We're going to use that idea to help us find horizontal asymptotes. So in this particular example, y is equal to 0 is the horizontal asymptote. Does anything change if I start putting powers up here? Suppose I had a 1 over x squared. Does that take away the horizontal asymptote? No, it makes the graph hug that asymptote quicker. 1 over x squared goes to 0 faster than 1 over x does when x is large. 1 over x cubed goes even faster to 0 than 1 over x does. So in general, 1 over x to a power is going to go to 0 when x is a large number. So fact, fact, fact. One over x to a power goes to 0 when x goes to plus or minus infinity. So let's look at something like this. Four x plus 2 over 3x minus 5. This particular example has both a horizontal asymptote and a vertical asymptote. Let's get the vertical asymptote first. Vertical asymptote is a line, x is equal to something. That x makes the bottom 0, but not the top. So take that factor on the bottom, set it equal to 0, and solve for x. Three x is equal to 5. That gives me x is 5/3. That's the quickie. To get the horizontal asymptote, we need to take the limit as x goes to infinity. For most of our rational functions, what x does to plus infinity is also what x is going to do to minus infinity. For most, I'll give you a couple of oddballs. But in this particular example, x is raised to the first power in both the numerator and denominator. So really, they're kind of growing at the same rate. And when x is big, 4x is probably just about as big as 3x. And I'm talking about big x's, 1,000, 1,000,000, a gazillion, a gazillion. Any made up really big number. So what I'm going to do to determine my horizontal asymptote is I'm going to put terms in here that look like 1 over x to a power. The x that drives the shape of this graph is the highest power of x, and in both cases, it's x to the first. So I'm going to rewrite this fraction by multiplying the numerator and denominator by 1 over x. After a while, we'll do this part in our heads. But I want to motivate what I'm doing. So I'm multiplying by 1, as long as x is away from 0, and it's way far away from 0. Then distribute that through there and simplify, and that gives me this expression. This x would cancel with that one and leave me a 4. When I multiply here, nothing cancels, so the best I can do is write that as 2 over x. Same deal here. Distribute there, the x's cancel, so I just have 3. Then I get minus 5 over x. So here's what I'm thinking when I take that limit. I have something that behaves like 4 plus 2 over infinity, and then 3 minus 5 over infinity. That's what I'm thinking. That's why it's in a cloud. But it's those terms where we're dividing by a really big number that we're going to get a bunch of zeros in the long run. So both this one and this one go to 0. And all I'm left out of this is 4/3. So we say the horizontal asymptote is the line y is equal to 4/3. The rest of them I kind of wrote down for you. I'm going to put black fingerprints on these. They're printed on the front and the back.
Thank you.
Taking limits to infinity help us find horizontal asymptotes. So the first 5 examples are the limits to infinity.
I understand.
I just love technology. Isn't that nice? All right, let me rub off my board and let's see how this. So the first example on this sheet says, find the limit as x goes to infinity of x squared plus 4x minus 1 divided divided by 2x squared plus 1. All right. When x is a really big number, it's the x squared that's going to generate the shape of this graph. And I have an x squared on top and an x squared on the bottom. So to mimic what I did over here, I'm going to take every term and divide them by x squared. So let's kind of speed that up. Let's just do that part in red. Take the highest power of x that appears, no matter where it is. In this case, x squared appears in both places. And divide top and bottom by that. Then reduce it. And then kind of analyze the value of this expression. If I reduce things, I'll get a 1 right here, a 4 over x here, and then the 1 over x squared there. That simplifies to 2, and that's to 1 over x squared. And remember, x goes to infinity, meaning all of those x's are representing really, really big numbers. Anything over a really big number is real small as 0 as you can make it. So as I take the limit, these terms that have the x's in the denominator are the ones that are going to go to 0. So I'm left with 1/2. That means the line y is equal to 1/2 is the horizontal asymptote. So let's generalize this. You've seen 2 examples where the degree on top was the same as the degree on the bottom. Can you generalize from 2 examples? Here both were 2nd degree terms, and we ended up with a limit of 1/2. Here both were 1st degree terms, and we ended up with a limit of 4/3. Do you see where that 1/2 and 4/3 comes from? They're the coefficients of the highest powers of x. So we can now do this just with our eyeballs and without marking anything down. If you have a function whose degree on top is the same as the degree on the bottom in terms of the highest power, then the horizontal asymptote is just the ratio of the coefficients of the highest power of x. So notice for f of x that has a numerator and a denominator, if the degree of the numerator is the same as the degree of the denominator, then the horizontal asymptote comes from the ratio of the coefficients of the highest power of x. Even if the degrees aren't nice whole numbers. Like for instance, if I had, I'm looking to take the limit as x goes to infinity. And say I have 4 times the square root of x plus 2 times the cube root of x. And I divide that by the 4th root of x minus the cube root. Now if I want to go the square root of x. Which x has the highest power on the top? The square root of x. And the highest power on the bottom? Square root of x again. The highest power in both cases is the square root of x. And so when I take the limit, one step that I can do is divide all four terms by the square root of x and see what reduces. But I know those two guys are just going to have constants. And the other one's going to have an x in the denominator. If those two guys are constant and the other ones go have denominators that go to infinity, then what's going to be left is the 4 here and the -1 there. And so our limit here is 4 over -1. And the line y is equal to -4 is a horizontal asymptote. If the degree on top is the same as the degree on the bottom, just eyeball the ratio of the coefficients of the highest power of x. So what happens if the degree is bigger on the bottom? Move the damn camera. If the degree is bigger on the bottom. So let's take kind of some version of that one. Let's just write the limit as x goes to infinity. And let's put a first degree term up here and keep that second degree term here. Now the shape of the graph is controlled in the long run by the x squared term. So let's divide everything by an x squared. When I simplify here, I'm going to get a 4 over x minus a 1 over x squared. This will simplify to 2 plus 1 over x squared. So I'm trying to put terms that look like something over x to a power, because I know when x is big, those go to 0. So in this reduced expression, those three terms that have the x's on the bottom will go to 0 when x gets big, and we end up with something like 0 minus 0 over 2 plus 0. So where I come from, dividing into 0 gives me 0, and the line y is equal to 0 is the horizontal asymptote. Do you think that's going to happen every time the degree on bottom is bigger than the degree on top? Is one example enough to generalize here? Sure, because we'll be doing the same crapola, right? So our second thing to notice is if the degree on top is smaller than the degree on the bottom, we'll call those bottom heavy. If my fraction is bottom heavy, then the horizontal asymptote will be the x-axis, the line y is equal to 0. So if the degree on top is smaller than the degree on the bottom, bottom heavy, then the limit as x goes to infinity of my numerator over my denominator will always give me 0. The bottom grows faster. And the line y is equal to 0 is the horizontal asymptote. If it's top heavy, there's no horizontal asymptote. The only time we get asymptotes is if the degree is less than or equal to each other. And then we don't have to do that dividing by stuff anymore. Now, sometimes we don't have polynomials, and so that's what I'm giving you here on number 2. We don't have degrees. I got a trig function and an exponential function. black than that one. The second one has the limit as x goes to infinity. Oh, that ain't no good. Oh, that one. I've got e to the minus x times the cosine of x. So one problem with this is that I don't even have a fraction. Well, trick on you, I do, because e to the minus x is the same as 1 over e to the x. That's the best I can do for an April Fool's joke. Best I could do. I tried. I thought all morning, what could I tell them? I could give you some sort of tragic story, like my pet mouse died or something. But then that might hurt somebody who had a pet mouse who really did die. So I couldn't do anything like that. So the best I could do is say, I don't have a fraction. Ooh, burn, I do. I put that e to the minus x on the bottom and make the exponent positive. Tell me everything you know about a cosine function. What's this, right? What's the most it's going to be? Very most it's going to be 1. And then in other cases, it's numbers between 1 and -1. So my numerator is always between 1 and -1. What about e to the x when x gets big? What happens here? What's graph of y is equal to e to the x look like? It gets big fast, right? Exponential growth is used as a phrase when things grow fast. That grows real fast. So it looks like a number between 1 and -1 divided by infinity. What's going to happen there? Take any number between 1 and -1 and divide by something infinitely large. As small as that, right? That's an example of a bottom heavy function. Which one grows faster? E to the x or the natural log of x? E to the x grows faster. Natural log of x is a slowpoke. So if I had something like this, and I take x to infinity, same thing happens. It's bottom heavy, grows faster. Exponential functions grow faster than polynomial functions. Logarithms grow real slow. There's not anything that grows slower than a logarithm in terms of your growing functions. All right, next one. Next one, number 3. I've got x to the 1.4 minus 1 divided by x to the square root of 2 plus 1. The -1 on the end and the +1 on the end, they don't mean a hill of beans when x is large. The size of this fraction depends on the highest power of x. And those two powers are pretty close in size, 1.4 and square root of 2. Got a calculator? Punch in the square root of 2.
.4, 1, 4, 2.
Blah, 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 blah. It goes on forever. But ever so slightly, it's bigger than 1.4. Square root of 2 is bigger than 1.4. So that makes the degree on bottom bigger than the degree on top. Bottom heavy. If the degree on bottom is bigger than the degree on top, the limit's always going to be 0. Bottom heavy. Even if it's big time bottom heavy or just a little time bottom heavy. Bottom heavy fractions go to 0 when x gets large. That looks like all the time we got there. The oddball one was problem number 4. I've got the same example, but x is going to plus infinity and x is going to minus infinity. That's going to be an example of a function that has 2 different horizontal asymptotes. So we'll do that one on Monday.